click through, that's fine. Alright, hello, I'm here to talk to you about the observability of interstellar objects in LSST. So we know they're going to be, so we'll eventually go backwards. Not forwards, there we go. We know that interstellar objects are going to be detected by LSST and they're going to tell us a lot about planet formation, but what hasn't been quantified as much is exactly what types of interstellar objects we're going to see or how easy it'll be to observe them. So that is the content of my talk today. So first of all, to describe the ISO model that we are using, so we're basing the velocities on the Hopkins et al. 2024 model, which is, we're now calling the Autotahi Oxford model. It's based on empirical data of the stellar population around the solar system. It's non-Gaussian, which is very different from previous predictions for stellar object velocities. And see Michelle Bannister's talk on Wednesday for more detail about that model. So basically we're taking that and the up-to-date or the most current LSST baseline simulation, and what we get is a catalogue of visits of ISOs within a field of view of LSST. So the next thing we have to think about is what affects whether or not these objects are observed or will be observed in LSST. So for starters, I'm just considering asteroidal type interstellar objects, which is great because 50% of the known population is asteroidal, so covering half the base. So there's a number of things that affect whether ISOs will be observed in LSST. The first two are a bit obvious. Distance and size, so these objects are coming in from infinity, so the closer they are, the brighter they'll be. I don't have to explain that to you. And then also size, the size distribution of interstellar objects, anyone can best guess. So what that will be will impact our observability as well. Second order effects, phase and trailing loss, so very different from our solar system objects. They're going to come in from all directions, there's going to be large phase angles, they're going to be faster, we're going to get more trailing losses. So this will have more effects on interstellar objects. And lastly, we've mentioned before, LSST is a ground-based telescope. There's going to be varying conditions, and so that actually does come into effect for detecting our faint interstellar objects. And to illustrate these effects for you, just briefly, here is a plot of visits of an ISO to an LSST field of view. All of these are the same size objects, so this is size independent. The three axes are the main effects of distance, trailing, and phase on the loss of apparent magnitude of the object. And you can see there's quite a distinct change from almost zero probability of detection right down to very likely to be detected. But that change isn't linear, it's very grainy, and that's also because of the variability of the sky brightness. That third order effect does come into play. So one question we had was, when we're trying to discover these ISOs, linking them together, will they behave on sky like we would expect for solar system objects? Most of our code is for bound objects. Will it work the same for unbound things? So here is a plot of sky motion rate versus acceleration, and things with small perihelions will end up in the top right of this plot. So starting off with a couple of planets, Neptune is the bottom left one, we all know and love, and these are simulated for the 10 years of LSST. And these are not detectable, this is just what the motions are, whether or not you can see the object in the sky. Next we add in some NEOs, and some of those start to do some weird things on the sky, especially in 2000 BD19, which gets very close to the sun. And our two known ISOs, we can add those on there, and those are simulated for 10 years around their perihelion passage, obviously not within LSST because they're far gone. And you can see that they behave like outer solar system objects, but also inner solar system objects when they came through. And so overlaid on that, we can now add our velocity model, the Autotahi Oxford velocity model that I'm using for these simulations. And most of the interstellar objects, their velocity space on the sky is consistent with objects that we do see in the solar system. So they're not moving strangely on the sky. They look like TNOs for a majority of their orbits, and they look like NEOs when they get close. So nothing too strange. Now, because they're also moving fast, we're going to see more trailing than you would expect for an NEO. So what I've plotted here is the trailing losses versus the effective distance for each image of an ISO in the LSST field, of view. You can see most of them are on the left-hand side of the plot, all the way at the top, so very far away. Most of them don't get close enough. So what do the trailing losses look like compared to bound solar system objects? So on the left there, objects at opposition have very, very small trailing losses, they're very far away, and it's sort of comparable to what we see for ISOs. ISOs are a bit faster, a little bit more trailing, but within 0.5 magnitudes mostly. But then when we look at things in the inner solar system at conjunction, and I'm aware you can't observe things at conjunction, but that is when maximum phase trail loss would occur, you can see that almost all of the interstellar objects that you would observe have trailing losses much, much greater than this. So trailing losses are really, really going to impact the observability of our interstellar objects. So all of that doesn't include size effects. So now we're going to introduce a size distribution and see what effect that has on the observations. And of course, two known objects, pick a size distribution. We decided to go for just a single slope power law and see what effect that has on our population. So we tested a variety of slopes and we'll see what happens. So starting from Q of 2.5, what I'm showing you here is a probability density function of the discovered interstellar objects from these simulations. So it's not the number of interstellar objects that are discovered, it's the probability that they will have a certain absolute magnitude. And so you can see that the peak here is around 16th or 17th magnitude. And as we change our Q value and it increases, our peak shifts to smaller and smaller objects as your slope goes up, which it kind of makes sense. It also gets narrower, and so we see less spread in the sizes of the objects that we're observing. So what we get when we quantify those peaks, we pick out what's the mode or median absolute magnitude and what's the spread of that distribution. You can see that as Q increases, the most common size object that we would see gets smaller. And so already, if you have a sample of interstellar objects from LSST, the most common size is going to give you some indication of what the size distribution is going to look like. The unfortunate thing is that our one known asteroidal interstellar object cuts through all of those size distributions. So 1i is actually, if it was detected in LSST, would actually not be a very helpful constraint just on its own. A bunch of 1i's probably would be. And so one thing we then asked was, well, how many interstellar objects would you need to be able to tell the difference between all of those distributions? So just some simple AD tests of running populations against each other. You find that to quantify or constrain your size distribution to within a slope difference of 1, you need 10 interstellar objects. So a sample size that is estimated we might get in LSST might help us constrain the size distribution a little bit. And we would need 50, about 50 to constrain it to within about half. So we're going to need a lot of interstellar objects. I think it's 240 to constrain it to within 0.2. So that's reaching a bit far, but maybe one day we'll get there. And so what happens for a slope smaller than 2.5, because we know that the Kuiper belt, which a lot of you are familiar with, has some shallow slopes. So why have I not looked at these for interstellar objects? Well, when I do that, for Q of 2, you get some weird effect where actually the most likely interstellar object we'll detect with LSST is the biggest one, which we don't really expect for solar system objects. So why does that happen? So for observing our solar system objects, we think about them most of the time constrained within an observable sphere. So the main belt is at a specific spot, so as the Kuiper belt, the Oort cloud stops at a certain point. The problem with interstellar objects is that the total observable sphere is the whole galaxy. So if you keep increasing the observable space, you're going to find more and more objects. So what actually this slope of 2 is telling us is that somewhere between 2.5 and 2, there's a breakdown in the single slope assumption. We can't say that there's a slope of 2, otherwise we would expect all ISOs to be massive in LSST. So there's something to do with the size distribution, or just the fact that interstellar objects are a unique small body constellation. Now that we've talked about size, what's the effect of colour? Because LSST has 6 bands, as you know. So previously I was just looking at solar type interstellar objects, give them all the same colour, and see how observable they are. So I investigated some different types, including your cold classical KBOs, and saw what effect does that have on discovering our objects. So this is again a probability density function, and observed ISOs are observed in at least one image. That does not mean they would be discovered by the Rubin pipeline. The discovered distribution is down the bottom, it's much smaller, they don't get discovered as often. But all of those lines represent the different colour types for these ISOs that I've simulated, and they all look about the same. So colour is not going to affect the size distribution of the objects that we observe, which kind of makes sense. That I haven't coded it to be dependent, so that's all good. When I look at a plot of the number of discovered versus observed objects in our simulation, so again observed, they're picked up in one image, but not enough images to be discovered, whereas discovered objects have those three nights of pairs of 15 days. You can see that there's a slight drop in the discoverability of the larger cold classical KBOs. It's only slight, but it's very interesting that they're slightly less discoverable than the other colour types. So I looked into why this was. So this is a wonderful rainbow plot of the number of images received by solar type interstellar objects throughout the 10 years of the survey. R band comes out on top, which is great for the solar system, the U band on the bottom, followed by Y. And so we can see if you plot this for the other types, the other colour types relative to solar, it's mostly constant, all down at the bottom where the object gets very, very small, that's a lot of noise. But what you can see is for cold classicals, the ratio of U and G band images to solar is much, much less compared to every other type of ISO. So they're not getting enough G and U images. So you think, okay, so fewer G and U images, that makes sense, they're just not going to be discovered. They actually have the same number of observations per object, so it's not actually a drop in the number of observations, it's just a change in the ratio of the observations per filter. And the interesting thing about that is that affects the number of tracklets that you're getting for your objects. So something to do with the different filters being observed for these objects affects how that gets translated into discoveries. And it's possible that because the cold classicals are much redder and not blue, you start detecting them in R far earlier than you start detecting them in U. So if you only have one image of R on one night, you can never get a tracklet. So that is why the cold classicals are slightly less discoverable than the other types, but only by a couple of %. And so to summarise, based on our current state of our modelling, interstellar objects behave like TNOs when they're at TNO distances, which is great, and they behave like NEOs when they get much, much closer, extreme NEOs. The number that we need to discover from LSST to get a decent size distribution constraint, 10 if we want a loose constraint, and 50 if we'd like a little bit more. A slope of 2.5 if we're assuming the single slope, which is just basic assumption at the moment, is unphysical because we're sort of punching through our observable sphere at the completeness never ends. And lastly, the colour of our interstellar objects does have some variability in the number that are discovered, but not enough to raise too much concern. Thank you very much.
I apologize if you mentioned this, and up here we can hardly hear you. So, based on your work, what is your prediction of the number of the ISOs that may be detected, and where do I1 and I2 fall in that prediction?
My work doesn't actually produce a number. You can apply a number density to these simulations to get that. And
well, you only have two.
Yeah,
What meaning is prediction?
Yes, there are a number of papers that have predicted numbers of objects. What we're doing is simulating different parameters for the population and how that will change what we observe. So if we see, I'm making predictions for the characteristics of the population as like a probability rather than an actual number. But you could get a number from this result. Okay, thanks.
Questions? If no, let's thank the speaker again. And